This is an AQA A-level chemistry topic. It's year 13, organic. We're on part 2 of amines. As always, I'm going to recommend that you pause, have a go at these for yourself, and then see how you do. In this video, we are going to focus on amines acting as Bronsted-Lowry bases, and we're going to compare their relative base strengths. Now, in particular, as the examiner's tip hints at here, we are going to compare ammonia to primary aliphatic and primary aromatic amines. Do be prepared to build up a good understanding of that. And there are close links here with work that you have done or will do in the acids and bases topic that will help to reinforce some of these key ideas. Let's take a look first of all at some of the key definitions. So Bronsted-Lowry acid and Bronsted-Lowry base. A Bronsted-Lowry acid is a proton donor and a base a proton acceptor. If I were then to think about the reaction that takes place with water, taking ammonia first of all, NH3 with H2O makes NH4 plus and OH minus, but obviously they come together to make ammonium hydroxide. Now we're familiar with the idea of bases being hydroxides, and this is helping you to see how ammonia acts as a base. Let's take a look at what happens with something slightly more complicated. We take ethylamine, we add H2O. It's actually exactly the same thing that's happening. The NH2 goes up to NH3 plus this time with our CH3, CH2 on there as well, and our OH minus. Now we're going to take a look at the base properties of ammonia, ethylamine and phenylamine. And we're going to start with this, go off and do some other work around it and come back to this particular screen a little bit later in the video. But what are your predictions at the moment in terms of the relative base strengths of each of the three that are listed? Well, I'm going to start off by drawing them out. I've got ammonia here, I've got my ethylamine, and I've got my phenylamine. All of them have got the N with a lone pair of electrons on. All of them, we're thinking about them in the context of accepting a proton, accepting that positive ion. And the question really comes down to which of these is going to be more attractive to that proton. Now we're going to come back, as I say, and explain all of that a little bit more later on. But before we do, we're going to jump back to work that you did in year 12 in the alkenes topic. And we're going to look at carbocations. When we looked at carbocations, we classified them as primary, secondary, and tertiary. We also knew that tertiary carbocations were the most stable, primary carbocations the least stable. Can you remember why? Well, I'm going to start off by again drawing these out. I've got my primary carbocation, my secondary and my tertiary carbocation, and I'm going to start to add a little bit of information to it. I've added an arrow here. That arrow represents what I'm hoping you were thinking about when you were going through this, the inductive effect. The alkyl group has lots of electrons, and those electrons can be attracted towards the positive carbon. But in a secondary carbocation, where there are two alkyl groups, that means there's going to be more capacity for electron releasing. That means more electrons moving towards that positive carbocation. And as I'm sure you can guess where it's going if you weren't sure for yourself, here I've got three alkyl groups, all of them electron releasing towards that positive carbocation. Now we know that this is the most stable. It's also got the greatest inductive effect with all of these electrons moving in. The greater inductive effect means we're essentially stabilizing that carbocation. It almost makes it less positive. And that means that if we think about it in the context of alkenes mechanisms, because it's less positive, it will survive long enough for the mechanism to move forward. But why are we talking about this? Well, let's now go back to amines. The inductive effect is also present here. Suggest why. Well, again, let's draw this out. I've got my NH2, I've got my lone pair, there's methylamine that I'm using for my example, and my inductive effect is electrons moving from the alkyl group towards the N. The question is why? I've not got the positive charge. I've got a lone pair of electrons there. But what we have got is a nitrogen which is more electronegative, which means it is better at withdrawing electron density towards itself from a covalent bond. So the N being more electronegative is why we will get those electrons moving towards it. So what impact will that have on the N with respect to proton accepting? Well, actually, this is the reverse of what we saw with carbocations. We're making that nitrogen more negative. We're putting more electrons around it. And because it's attracting protons, that's going to make it much more attractive. What about in an aromatic amine? How might the basicity of phenylamine compare to ethylamine? Well, again, let's draw this out. I've got my NH2 coming off my aromatic benzene ring. This is not about the inductive effect. We've actually got an incredibly stable delocalized ring of electrons here. And what actually happens is the lone pair on the N is close enough to that electron ring to almost get absorbed into it, to become an extension of that stable delocalized ring. That makes this particular amine far less electron releasing and therefore far less proton accepting. So we've got lots of information there that's going to now help us to go back to this screen. I'm going to rejig it ever so slightly, and I'm going to go from strongest to weakest. My strongest base out of these three is ethylamine. Phenylamine is my weakest base. Ammonia sits in the middle. And just as a brief reminder of why. Ethylamine is the strongest base because of the inductive effect, because the alkyl group is electron releasing, making the nitrogen more attractive to those protons. And as we've just saw with phenylamine, the lone pair on the N becomes part of the delocalized ring, making it far less likely to accept a proton, making it a weaker base. Ammonia sits happily in the middle. Going to add a little bit extra here just in case there's a question that comes up that decides to challenge you a little. And that's to consider what would happen with this. I've got my NH2 and I've got a benzene ring, but I've got a CH2 between it. The important thing, this does show the inductive effect. But the lone pair is too far away from the delocalized ring. So for this particular structure, we would be thinking more along the lines of what we say about ethylamine than we are about phenylamine. That takes us to the end of part 2 of this series. Thank you for listening, and goodbye.